Hello, dear students. Today we have second lecture as part of our combined course of medical informatics with biophysics. Second lecture on topic which is related to medical informatics. In this lecture, I want to provide some brief notice about medical images, introduction, what is medical images, and some basics on analysis and processing. Topic's very broad. Actually, its entire course would be not enough to cover it, but you will meet with this question related to medical image analysis during your further education with clinical subject and so on. So, in this reason, today we got only introduction with some emphasis on information technologies could be applied and being applied in this area. So, major topics of our lecture, including understanding of place of imaging in medical science, then we will refer slightly to biophysics with question about how to medical image could perform acquisition of medical images, and I made some notice on analysis and processing, and finally we'll introduce for you theoretical background of picture hearing communication system as well as digital imaging communication medicine standard for medical images exchange. When we talk of imaging as and this is a place in medical science, which is quite important in modern time, we should consider that it's a very multidisciplinary field, and also I want to pay some attention about what actually digital image is, what is image modalities we have on the medical images, and what kind of information could be obtained with medical images. So, generally speaking, imaging the essential aspect of medical science for visualization of anatomical structure as functional and metabolic information of the body, which is available, thankfully, for recent advances in imaging techniques and information processing. So structural and functional measurement of human body is important to understand the anatomy, physiological properties, function of organs, and behavior of whole or part of organ on the influence of normal physiological condition of diseases. So, development of imaging instrumentation has inspired the evolution of new computerized image extraction, processing, analysis methods for better understanding and interpreting of medical images. And actually, recently, intelligent or model-based quantitative image analysis approaches have been explored for computer-aided diagnosis to improve the sensitivity and specificity of radiological tests involving medical images. As mentioned that medical imaging in modern time is a multidisciplinary field because it's involving current understanding and existing knowledge of physiology and anatomy structures, which forms a sort of backgrounds of those of studying principles and specifically a physical basis of those imaging methods which could be used for further studying of different anatomy or of existing anatomy of physiology structures, which should lead to development of new techniques and instruments, or assembling from existing components, or just selecting existing imaging device which further will be used for image acquisition. with our given target, and also we will be capable to retrieve image information in digital form. It's become available for processing with computer system, so we can again employ different existing method approaches models to retrieve some important diagnostic information from those raw image data, with aim to make decision about possible diseases and development treatment plan, performance apply to user, and then again using medical images to supervise of results and obtain some again decision about retrieving more images, and so on. So cycle will be repeated again. So actually all these things I already noted, except that computerized image construction, processing, and analysis methods have been developed for medical imaging application, which requires specialized knowledge of specific medical imaging modalities. It's used to acquisition while medical images. And also application domain knowledge has been used in developing models for accurate analysis and interpretation of our data, which obtained from in digital form. So radiological science in the last not so long 4 decades have made revolutionary progress in medical image and computerized medical image processing. And here is given list of advanced approaches of different multidimensional medical image modalities, which include the usage not only X-ray techniques like computer tomography, mammography, and so on, and other different application, but also more specialized solution like nuclear imaging in form of positron emission tomography or single proton computer tomography, also radio analysis, which give us not only anatomical information from magnetic resonance imaging, but also it's even more important to retrieve functional MRI images, which will depict physiological processes which fall into organs and tissues, and a modern approach for using ultrasound medical images, which not only allow to retrieve not only static but dynamical live images. Speaking of image modalities, we can classify medical images according to energy source which used for images, like external, internal, or combination of both. And here is listed the appropriate method, corresponded method which reflect these types of modalities. Like when we talk about external images, usually we're talking about usage of X-ray imaging, but also ultrasound and optical transmission imaging. The only one representative of internal energy is nuclear positron emission tomography method, and MRI and also some few specific kinds of fluorescence imaging and impedance imaging use combination of both external and internal images. So it's already spoken this slide. I think it's not necessary to point on it anymore. And here is time to make some refreshment and updates on your biophysics skill, to remember that when we talk about our capabilities to absorb electromagnetic radiation spectrum, it's limited only with visible light, with very narrow band of entire electromagnetic radiation spectrum. So, and what is actually benefits with modern magical imaging techniques, that we can bring images, we can bring information which obtained within different range of in electromagnetic spectrum, different range of frequencies and energies, which are represented by like X-ray, gamma ray imaging, which is ionizing radiation, and MRI, which is actually with aim to modify this information in such a way that make it visible for our eyes, for our sensitive capabilities. So here is how we combine this into this all together. And here is kind of information, again, speaking continuously about modalities and kind of information we can retrieve from by employing modern medical imaging techniques from body. It will be kind of anatomical and functional metabolical images. And here is again, we place it all together with energy kind of ionizing, not ionizing approach for retrieving images, wavelengths, and so on. So all this here is how it's arranged all together when we talk about like retrieving anatomical images by using gamma rays and X-ray imaging, and functional images with conventional optical imaging, like using employing endoscoping techniques, fMRI, and so on. So here is all this together, all modalities together. Now move into second question of our lecture, principles of acquisition, analysis, and processing. So significant part of this question represent topics from biophysics. So I will pass it relatively quickly, and will make only emphasis on those aspects which is corresponded to information technologies. Okay. Generally, when we talk about biomedical image processing analysis system, general purpose of biomedical image system, it's always consists of three parts. So first of all, image acquisition system itself, which aimed to convert biomedical signal, radiation, current information of interest into some kind of electrical signal. Not necessarily digital at that point, but modern solution for those types of system produce digitized signal at output. Then computer unit, which designated to first of all storage of this digital signal in form of different digital image files at this point, in fact, and performing necessary processing operation. And of course, such unit usually will be equipped with with display equipment. So is that we're talking about conventional laptop, desktop or laptop computer, or is it we talk about something more specific, or even we can consider it as like separate units, for example, mobile ultrasound system, when we have acquisition system and data processing unit embedded together, when as computer system unit and display environment, usually tablet or even mobile phones has been used with special application installed. So here is important point, that digital computer display equipment could be at this role could be used conventional desktop, laptop computer, or mobile device even. But they has to be present. That means they could be represented mostly as software solution, but they must be present. and like image acquisition system, which include like energy source, sensors, and some analog to digital converters, represent hardware part of biomedical image processing system. Before we move forward, it would be important to make a notice what actually image is and what is digital image is in fact. So when we consider any kind of image, at this point, I'm not even speaking about digital image, any kind of image, we have to consider it as any flat image as two-dimensional signals. So when we have function of coordinates, f from yx, which represent each pixel element of picture, picture element, and those pixels represent like will illustrate something like elements of color or with given intensity, or it could be, for example, if we talk about monochromatic image, so it will be intensiveness of gray level, and so on. Actually, size of picture according to XY coordinates will represent resolution. Resolution that's given quite low. Modern time we are talking about megapixel and so on. Speaking of our smartphones, of course, but general principles is working this way. And when we talk about converting, capturing of digital image. So in this case, various types of digital sensor has been used. Here is given example of cooperative CCD, charge cooperative devices, which converts visible light like energy which comes in form of photons from visible lights, or it could be any wavelengths from given electromagnetic radiation spectrum, and it turns it into electrical signals. At this point, of course, it's analog level. Again, these principles useful not only for visible light, but any wavelength with proper adjustment for CCD device characteristics. And actually, if we talk about depending to some approach to assembly of CCD device, it could be used for registering black and white, grayscale images, or with cells adjusted to register different wavelengths, like shown here. We can, let's say, a matrix which will be capable to register full color images. So actually, in fact, it's how a camera in your smartphone works. Here is actual example of digital camera, how it's work and how what it consists of. Same technology, same structure is applicable for all medical imaging diagnostic equipment, and actually, as outcome of the sensor, we already, let's say, digitized signal. So again, it's this feature could be depicted by the following diagram, which summarize methods for retrieving digital image. We have some kind of illumination source, which produce energy to analyze an element. And this element we understand or visible part of human body or some internal anatomical structure when we talk about attenuation of radiation to human body. Then those wavelengths consolidated by some imaging system and being projected to the image plane, to the surface of sensor, which formed by independent sensitive CCD sensitive elements. And here is we have as output we receive. So here is what had been projected onto surface of the sensor array, and here is this side, and here is we have what kind of signals we have retrieved from this array. Of course, as you can see, we have significant difference. We have our logical representation of our data, which represent information about object we want to get image of this. It has like some different form, adjusted form, which is adjusted by dimension of matrix elements. So here should be obvious major problem of digital imaging formation. We should have matrix of element with sensor as smallest as possible, and we should have matrix with number of elements as greatest as possible in order to retrieve high quality of image. And actually, it's the same problem like you have in your smartphones. And here is just enlarged case when we have, so at left side, those things which have been projected on the surface of matrix element, and at right side, it's visualization of matrix array response. So those signals produced by sensitive elements, visual representation of signals which produced by sensor, each sensor of sensor array. At left side, we have continuous signal. At right side, we have digitized version and discrete signals retrieved from sensor. So here is, we can summarize it again in form of matrix in this case. As input above, we have continuous matrix of continuous signals, and at output, we have matrix of discrete value which represent or like each color of value of color per each channel, or intensiveness for grayscale images, and so on. So it's also a reason why sometimes digital images called matrix images, because in fact it's square matrix of numbers. So let me summarize this in this way. In the following diagram, here is we have live medical images at top left corner, and here is how this like small part we want to enlarge and analyze in details. Here is at the right side at the top we have how this transformation being performed, how we perform digitalization, some sampling of our signal data when we have analog sine wave, which represent our like one slice of our signals, which fall on one row of matrix, one row of sensor in matrix. And here is we will see in the equivalent results value produced by each separate cell in our matrix. And at the bottom, we will have actually, first of all, we will have our actual matrix, which contains integer value for which reflects intensiveness of signal for each particular cell and each particular pixel. And at the right side, finally, we let's say our digital image. We let's say our digital image being displayed on a computer screen. So how things works. Now actually pass through some real techniques which used to create, to acquisition and create digital medical images. Let's consider transmission images. Basic principle, of course, radiation treatment passed through the human body, and most known techniques is, of course, X-ray radiography and computer tomography, which is based on the same physical approach, but also infrared, optical, microwave imaging techniques represent same physical principles. So, of course, when we talk about X-ray imaging, history had been started about 130 years ago when Conrad Hand create this device and be capable to register fast image which depict anatomical structure of hand. So actually, beam of X-ray directed to patient onto film, and film provide measure of radiation in tissue. Here is how conventional radiography works like in this diagram shown in the real system. But for us, most interesting not X-ray techniques itself, which is still very widely useful and very important, but major advances which it's allowed to achieve, that's creating computer tomography imaging. In this case, when films had been replaced with X-ray digital detectors, then after very specific processing of registered signals, we got capabilities to retrieve images, computer tomography images, which is, as you can see from this picture, or this screen depicts major features of these images. We collect information in plane of rise past through human body, but we reconstruct images in perpendicular direction. So generally, tomographic, it's a graphic representation of Kuto slice and implies formation of two-dimensional cross-section images free of blurring from structures not in the place of interest. And computer tomography is formation of tomograms of X-ray adsorption coefficient by methods of reconstruction from recorded projection. So that's point I already revealed. We reconstruct and visualize images in other projection than rays pass through human body. So here is actual 7 years necessary to develop first generation of X-ray computer tomograph and was given Nobel Prize for this, and it required computer expert and physical scientist. And actually, modern time, multiple generation of computer tomography already developed and in use in many clinics. Even in Ternopil, we have few computer tomographies already. So modern systems allow to visualize not only two-dimensional structures, but visualize three-dimensional structures. But major limitation remains the same. It's mostly useful for relatively hard tissues like bones and so on. And it's very not easy to retrieve some useful information, for example, for soft tissues. Let's start with some information technologies background, which is necessary to retrieve computer tomographic images. So here is at the part of the slide, we have visualization of conventional X-ray imaging when on the film or computer screen, in case of digital X-ray, had been registered changes in attenuation of energy when X-ray passed through human body, passed through human organ. And actually, with adding some specific computer processing, which I will further explain it a little bit, we will, let's say, have capabilities to retrieve information from each slice of it in 90-degree projection. So what was necessary steps which allow for us to achieve creating of computer tomography? First of all, of course, its achievement in physics. End of 19th century, inventing of Conrad and Hen, or we can discuss it and should not remember about Ukrainian scientist Ivan Polyev. Anyway, next important steps, its achievement in mathematics. So-called Radon transformation, had been made at the beginning of 20th century. And it's spoken about, mathematical theory, it's spoken about relationship between polar and Cartesian coordinates and working with projection. Then, of course, it was necessary inventing of digital computers at the end of Second World War, 1945, in fact, and their advance into more powerful system, which allows to combine previous item together, so which allows implement advanced mathematical transformation called forward and backward Radon transformation with digitized data from X-ray imaging, and it led us to 1960s, to end of 1960s, and development of computer tomography. So we need these all three components: physics, mathematics, and information technologies. So here is how actually we deal with processing, how fast generation of tomography works. That we have sensors and X-ray sources, which has been around patient body and register attenuation at each angle, at each point. Of course, modern tomograph works different way, but will be later about this. And now move into necessary mathematical principles. So first of all, what we will, let's say, with when we will register changes of attenuation of X-ray when they pass through body, it will be actually information for Radon transformation. It would be information about projection. So here is we have. In fact, what we will register will be this data, G from S theta. So that things we will, let's say, after we made registration of energy which is carried by X-ray after passing through human body. And actually it's given equation represents how its relation to original coordinates of xy as function of, in this case, it will be density of element inside the human body. So we got this information the right side, and our goal is to construct its original. So here is actually what is exactly Radon transformation. How does this data look like? and with different number of projection, depending how we made the registration for each TAN file and to degree how accurate our information will be. And actually to retrieve our information about original structure, we need to revert back radon transformation somehow. One of the approach is employ Fourier transformation, which is quite similar for given equation and much simpler, could be processed with computer system algorithms. So here is given necessary mathematical statement for this. So, and actually what we are going to do when we want to turn from radon transformation into Fourier coefficient, then we are going to use backward Fourier transformation to create backward radon projection. Okay, so here is again projection theorem, which is state about relationship between our coordinates in polar system. And finally, we perform backward radon transformation using this projection theorem, so filling two-dimensional Fourier transformation data matrix with one-dimensional Fourier of radon on our different signals, then perform inverted, and we then need polar to Cartesian grid conversion for discrete scenarios. And here is what actually do we will retrieve then our reconstructed images. So a little bit complicated. Yes, it's really complicated principles, and that things which had been done anytime when we retrieve computer tomography images. And here is this way we come to this equation, which in fact represent backward radon transformation and allow to retrieve this XY location for pixel inside our of image, which will represent internal structure registered by X-ray imaging. So here is this red dot, results of reconstruction. Actually, each one is back as well. So starting from this equation of radon transformation, starting from getting this information as results of X-ray scanning, we are going to reconstruct this function, which will represent our original anatomical structure. And here is how it actually works. Those famous experiments of inventors of CT scan, they just scanned two cubes, and here is example of spinogram which represent radon transformation, and backward radon transformation give us original image. And here is difference between generation of computer tomographs. Last generation even have not using moving part anyway. That's just arc of sensors and detectors had been used, so they work the following way. As you can see, sensor and detector rings has been employed. Different techniques involved to make a reconstruction faster. For example, spiral computer tomography, which allow to pass to make patient be driven through CT machine constantly. No need to stop at each point to take each slice. And so here is original slice by slice scanning, and spiral volume scanning still allow to produce high quality images, which allow to give us, to retrieve us something like this. So we can create three-dimensional visualization but such as I'm lacking of true three-dimensional like holographic screen, and probably you as well, we have no chance then make projection of the three-dimensional dynamic image on flat screen, and again we observe a series of two-dimensional projection. So that's also things important to be remembered about what we actually see. Same information technology principles also had been used for other kind of visualization, for example, magnetic resonance images, which utilize another physical principles, like spinning of hydrogen nuclei and strong magnetic fields, which produce signals which could be registered with detectors, but after that, given information processed in very similar way as I had spoken about computer tomography, and as a result, we have capabilities to register similar stacks of two-dimensional images and even construct three-dimensional images as well, of course. But this time, this techniques much more better useful to visualize information about soft tissues. Soft tissues. So multiply modalities available under MRI, like angiography, spectroscopy, functional MRI, which specifically very useful to visualize processes which flow, especially in especially for study brain functions, and so on. So here is example of magnetic resonance radiography. Actually, my previous drawing, my previous visualization, at right side, we have in fact MRI images. At right side here, we have computer CT images, which represent bone structures of skull. Here at the right side, we have visualization of MRI image. We have vessels, blood vessels visualized here. Okay. Again, different physical principles, but the same approach for processing data, nuclear medicine, which provides direct representation of metabolism for function in the organ structure, you may imagine, and a single proton emission tomography, proton emission tomography has been used. So again, difference in physical principles, difference in imaging equipment, but speaking of computer part, information technology, and imaging processing approaches, they are pretty very the same. So here is we have. And again, advances and achievements in information technologies allow for us modern time to combine images which is retrieved different way. For example, and combine MRI and PET images and formulate so-called multimodal digital images in this case. Speaking of ultrasound images, again, it's propagated into the patient from transducer placed on the skin and backscattered echo signals recorded by the same transducers. So invented in the late 1990s. Modern time, again, sensor bucket by computer system, and image could be reconstructed even in form of dynamical visual images. But physical principles again had remained like barely untouched from the time of inventing. Major changes have been achieved there at this stage. Stage of image processing, and we can move from flat two-dimensional images into not only three but dynamical images. Okay, Now move into next question of our lecture, into image processing system. And so what this system is responsible. So after we perform acquisition, after we registered those changes in electromagnetic radiation and converted that changes in form of digital signal, it's time to process it before it will be visualized. And actually, I already talking about some right time about processing when I had been spoken about construction of three-dimensional images from two-dimensional projection from CT. That's actually all these steps. But right now we consider it more detailed, some points in more details with aim to distinguish some specific tasks in image processing, like pre-processing, segmentation, detection, and analysis. So actually, we can split it into, better will be to split, to convert previous diagram in more advanced, more extensive chart, which will again summarize acquisition digitalization as considered as a step formation of images, of medical image, then basic processing, which usually had been done by the same equipment which performed digitalization, so calibration, registration, transformation, filtering, all these features had been applied during instantly after acquisition of image, and then medical image information system has three parts for what has to be done. It's visualization on screen, or perform automatic analysis, guided or by a physician, or guided, fully automatic. And third way, what we can do with actually our image data is management, in meanings archiving, retrieval, and exchanging via communication channel. So let's check again. I have already spoken about computer tomography, about very advanced transformation, but move back to some basic things. When we talk about basic transformation, even if it register flat two-dimensional medical image, take a photo, for example, of skin or so, we want to make, for example, enlarge our picture to better see some specific details. So all such as, we have to back again, such as any such as a representation of our digital image, logical representation. It's matrix, or it's square matrix. Each element represents single pixel of image. So any transformation of medical image, any image on our image processing methods, in fact, will be reflected as matrix operation. It's matrix operation. If you want to turn it, turn image for some degree, it will be specific transformation of matrix, like shown here. If you want upscale, downscale, it will be yet another transformation, and so on. So, next, pre-processing involves filtering, denoising, registration, and enhancement. Here is given filtering, scaling by different levels of column, and pre-processing algorithms only used median filter, mean filter, wavelength-based denoising filter, image registration, and so on. Of course, those things usually implemented automatically with different diagnostic equipment, or have some useful, user-friendly comments like improve contrast, brightness, contrast, and so on. But their nature is matrix operation. And here is example of what filtering actually is. So under filtering, we understand process when each output pixel depends to input one of and all around. So we apply for each pixel in output, we apply some specific function which involve counted features of pixel around given into original image. This way we can, here is on screen shown how we actually decrease image. We take into account, let's say, 5 pixel instead of 1 and calculate something like average to depict our case. Same way we enlarge our pictures, just change we take our round pixel, calculate new, and we have goal to calculate more pixels than in original image. Okay, and so here is example of different functions which represent different filters. As I already said, that most of imaging analysis software allow to apply these things without formulas. So you only need to use special tools available in this application. For example, in case of ImageJ, very quite common application to analysis and processing of medical images, we have some tool like smooth and filters under process menu, and which allow for us to do the same thing. So smoothing, it's same as applying medial filters. We have the same outcome for this process. Or feature enchantment. So here is, we have another case of mammography images. Here is the left side original, then at the middle we have adaptive contrast enhancement algorithm applet, and at the right side histogram equalization method. So depending on the goal of visualization, different we can apply different methodologies to identify potential pathological elements there. Okay, next step of image analysis, it's segmentation. So it means delimitate object, so they are detected. And here is its question is finding boundaries of objects and identification of what kind of we have. This way we can identify and separate like vessels, livers, brain components, and so on. Yet example of performing segmentation analysis, and you will applicate it to do it during your practices. It's creating a contour filter using Mavis Web application, which allow us to identify borders of different type of tissues within brain. So here is how it could be solved with this tool. Again, plenty of segmentation algorithm available, which is object for subjects for studies on the digital imaging processing area. So here is we have Car-Means fuzzy, neural fuzzy, neural network-based segmentation, shake algorithms, and so on, thresholding segmentation. So number of approaches available to deal with these things. Again, if we talk about practical application with specific user with software dedicated to being used by conventional position. So here could be something like I just shown with segmentation lab. There is no points about exact algorithm had been used there, but in fact it's implement one of this. And this approach allows for us to perform a very advanced visualization of data we had retrieved, we have already retrieved from our diagnostic equipment, for example, from CT scans. So here is we have our original image, and by using different segmentation method, we can visualize only soft tissue or in combination with bones, and we can make our specific subtraction to visualize only those areas we are interested in, and so on. And detection, find the location of object of interest without prior knowledge about their existence, location existence. So useful for detecting like abnormalities, first of all. Here is shown example how possible to detect something unexpected, inclusion unexpected components within given structures. And so here it is, we have how it could be useful, for example, for automation. At the bottom, we have our original image, and top we have entitled elements with after identification and detection of necessary elements. And again, when we combine, multiply images from different sources, different type of medical images, become very useful for identification of possible pathological objects there. For example, here is we have some kind of tumor here, which barely visible on CT image, but extremely good could be visualized with PET image, which is practically very poor itself. But when we combine this, it's give us quite large number of information to be analyzed, and this way detection could be employed, automatic detection could be employed to retrieve information about possible pathological elements there. Same way, differentiation for recurrent malignant disease from therapy and its changes. And here is we have how both MRI and PET images could be used at the same time. Another approach, again, the robotic retinopathy ultrasound, the image of bottom of the eye, can give us this information here. Okay, now move into past, present, and future of image processing. So when we talk about paradigm of medical image processing, so those part left side, we have that things which is already considered as solved once and for all time, like principles of registration of digital images, manipulation by pixel, visualization, storage, data exchange. Still on the development and usage is cohesive relation. It's works and studies still continues on creating multimodal, multidimensional images, which is actually referred to future as well. Automatic segmentation, classification, and measurement of image. So these two parts of tasks still important, and still IT solution had been developed there. And future considered as usage of formation of multidimensional, multimodal images, and use it for automated diagnostic and treatment, computer-aided diagnostic, computer-aided treatment. Okay, now time to move into third question for our lecture. Information system, which is used to managing of medical images, picture human communication system, and also some international standard which allow exchanging which establish probabilities for exchanging medical images, DICOM. So, picture human communication system, computers are network dedicated to storage, retrieval, distribution, and presentation of images. And they are actually almost can't be separate from DICOM, because all PACS system must support DICOM feature. So, aim of PACS is to replace hard copy-based means of managing medical images such as film hues, and expand possibilities of such conventional system by providing capabilities of off-site viewing and reporting, including distance education, telediagnostics, and so on. And also, again, it's share data and access multiply physician for the same images at the same time, creating single point of access for images and association data, and so on. Actually, it's an essential part of hospital information system at modern time. So, solution, how it could be built in, again, this time it will be, not this slide depict only possible solution, or rather even some essential components of typical PACS system, but a real solution could be composed by all of this or part of the system, but usually we will have something like central system, workstation, which central server which perform data storage and data management operation, workstation which has to be used by physician to access data from local network, and remote web-based solution which allow to establish remote communication and remote access to the picture data. So in fact, PACS, aim of PACS, it's create central access point for different kind of medical images, primarily by using DICOM format. And here is example how they could be presented as separate system, PACS here at left side, or being embedded into general hospital medical information system. So I already mentioned that essential things for PACS working properly, it's their support of digital information in medicine, or standard for handling, storing, printing, and transmission information in medical images. So it includes file format definition and network communication protocol description that allow medical image data being fast file directly transferred by computer network like TCP/IP, and then stored and retrieved by any compatible device or software from and into DICOM files. DICOM files. So actually, what we can do with DICOM, that share medical images over DICOM or Health HL7 standard compatible network, and access and deal with such images from different places, by using different devices, with purpose not only, for example, visualize, but even, if necessary, create hard copy printing on printers, say, to disks, and so on. Okay, National Electronic Authorization for United States holds copyright standard, enable integration of scanners, server station printers, and so on. Also, with aim of special software, we can even add support for non-DICOM devices to create DICOM images and then share over DICOM network. And major features, it's that's DICOM container composed of data set, and actually we have few data set. We have image container inside DICOM file itself, and we have all necessary description attributes which contain information about as many as possible about that image. So when, where it has been taken, what, from which patient, so some identifications, uh, information about physician, if any conclusion had been provided, so those conclusions could be attached as separate attributes and so on. So all these things extend the just image and turn just simple digitized image into actual medical document, in fact. So here is we have quite large diagram which reflect components and entities under DICOM standard. So here is we have network components, and actually only at right side that part of DICOM that physicians actually most time working. That's DICOM file, save it onto different media from computer hard drive to like removable media, flash drive, card, optical discs, and being transferred between different facilities. This way, physical way. Of course, because most efficient way, it's sent via network. But again, physicians most likely work with images at given medias. And here is some examples of few 3D-com viewers. There is plenty of such tools. In fact, we are reaching end of what I had to say about introduction to medical image. Thank you for your attention.